All right, welcome everyone to week 2. It's good to be in a place where it is warm. It was cold where I was, and I don't like cold weather. I did not move to Houston to be cold. And I live in kind of an old house, and I can't ever get it warm enough. So I either destroy the planet by just wasting lots of fossil fuels, or wear 2 sweaters and use a space heater and just try my best so that I never get warm. So I'm happy to be back. We're here today. It is very nice. Okay, so today we're going to continue on. We finished chapter 1 last time, and I've had to throw out half my homework problems because they require access to databases and policy statements and charts that are all offline because of the U.S. government shutdown. I never really realized how many things were stitched into things that they had on their site. There is a website I will use this opportunity, however, to show you, which is run by a friend of mine that it occurs to me I haven't talked to in a little while, but let me show. Does anybody know, let me see if I can find a couple of cartoon characters here for you. Has anybody ever heard of these guys? It looks like Snoopy. It's a dog, but let me see if I can find an old picture. Here it is right here. I had a t-shirt of this in college, so this tells you how old it is. This comes from a cartoon that was run in the 1960s in the United States and maybe into the 70s called Bullwinkle. Anybody ever heard of that? There's a big moose, and he was kind of a friendly moose, and he spoke like this, and, "Hey, Rocky, watch me pull a rabbit out of my hat," and stuff like that. But it was made during the Cold War between the United States and the Soviet Union, and so these guys were always battling Boris Badenov and Natasha. She was an evil woman from Russia. So it was one of these deals, but they also had a couple of other little cartoons in the middle, and this was one of them. And the dog is a genius. He's like the smartest creature ever, and he invents this machine to go backwards in time called the Wayback Machine. And so these guys visit different times in history, and they teach you things about history which are completely sarcastic. I mean, if you just sort of accept them, they're historically accurate, but they're always very sarcastic. If you're an adult, you can enjoy the show too. So this is a cartoon where both the adults and the children enjoy the show. Like Bugs Bunny. You know, Bugs Bunny is kind of a smart aleck, so kids like it, but adults kind of like his attitude. So why am I showing you 1960s cartoons? Because the Wayback Machine was the name given to a project by Brewster Kahle, who I worked with on some huge supercomputing stuff at MIT back in the 80s, I guess. And the Wayback Machine is the name he gave to a site that he built called the Internet Archive. So has anybody ever heard of this site? So it's a little bit like Wikipedia in that it's nonprofit and freely available, and people donate to it. I've already donated, so you don't have to feel guilty. I donate regularly to this stuff. But it takes snapshots back to 1996 of websites. So there's a few things to mention. Just because the U.S. government's web is down, I can still get their documents. So if I want to look in here for FCC spectrum chart, I can't get it from the FCC, but I can get it from this 350 billion web pages. So I just have to look through here and find one that I like. Worldwide Gadget. And I'm not going to do it right now, but a lot of people match those phrases because they've grabbed pieces of it. If you have the actual URL that you're trying to get to, like the Spectrum dashboard here, the website that I typed in to get that was, let's look here. Come on. You can do it. There you go. Okay, what I want to do is copy this and then go back over to the Wayback Machine and type in the URL this time. And so here's all the dates where they've taken a snapshot of that website. And so you can go through, these are the ones for 2018. They haven't snapshotted it in this year yet. If I want to go and see what it looked like in 2014, I can do that as well. I can look to see what did this site look like at 4:11 a.m. on the 10th of February in 2014. So if you put something up on the web and you regret it, and you take it off the web, too late. Probably Brewster has grabbed it, especially if there's been very many references to it. You'll find it. So this is what the website looked like back then. The interesting thing is some of these links they've grabbed, but some of them still work. So they don't, have to just pull them up. So this is a way to get a cached copy of a web page. The other way to do it is to go to Google and ask for the cached copy of the web page. Google also caches the pages because that's what their spider crawls to index things. And that's what they use to show you previews. So it's a cool site. If you had something on a web page and it's now gone, this is like my life. I put things in homeworks, and then the next semester the freaking things disappeared because somebody changed the URL. I just go, Brewster, save me, help me out here. And when he does, I throw him like 20 bucks. It's like, burp, burp. He like barks, and I throw him a treat. Right? So anyway, he's a really brilliant guy, and one of these days, if I can figure out how to tie what he does into a networking class, I'll have him come and give a talk to us. So I'll put him on Skype or something like that. So I wanted to show you guys there's a lot of good old network material out on the web that's moved or it's gone or whatever, and this is kind of the archive that's out there. And you should fund it because it's usually really, really slow because they don't have enough server capacity. They have massive storage, and one of these days I got to ask him how he pulled all that off. Okay, so what we're going to look at today is following up on some of that material that we did last week, and I still owe you guys a homework. We're going to look at the OSI and the ISO model, and we'll look at the TCP/IP model from the IETF as well. We'll look at the differences between them. We will have to deal with a little bit of OSI here because it's the standard that now people try to fit TCP into. They try to understand how TCP compares with other models by using the OSI model to point out things like, well, TCP's collapsed layers 6 and 5 down into one layer, for example. Okay, so that's what this chapter that he wrote. Has anybody downloaded the PDF of the book yet? Have you guys found it? So it's out there. I think I have it in your folder. Let me go look and see. This is your folder. Yeah, I did. I put it out there. Oh no, that's the wrong edition. How interesting. Well, since I promised you I was going to do it and I didn't, let's go do it. Deal? All right. Here it is. Okay, it'll take it a few minutes to sync, but that still looks like the same one. No, yeah, this is it. So here's your textbook. It's out on your Google Drive. So if you haven't also been to the Google Drive yet, you need to do that. The link to the Google Drive is in Blackboard, and it's also in the material that I've emailed to you guys in the syllabus. And if you need me to, I can put the QR code back up for you guys. But starting with this chapter, we're actually going to start looking at things that are a little bit more technical. You will need the PDF to answer some of the questions in the homework. Or you can Google for the answers as well. You'll probably find what you need that way as well. But I want you to start getting used to the notebook. It's a strange, to the textbook. It's a strange textbook. It's like most textbooks printed in black and white and one other color. So lots of times the other color is like blue or green. This book's other color is pink. I'm guessing it's probably the only textbook you'll ever have where the other color is pink. So you also want to look at the PDF for that because it's kind of flashy. It's a little interesting. Okay, so we already know what a protocol is. It's rules governing how we exchange information. So we talked about maybe the Queen of England. I usually bring that up. So there are specialists in protocol who sit down and list out exactly what's going to happen when two heads of state meet. In extreme details. Who's going to open the car door? What hand are they going to use to do it? Will they have a weapon? Which side of their body will it be on? Will they be wearing gloves? What color? Is there something embroidered on the glove? Will they touch their hat with their left hand while they open the door? How far will they open the door? Is there someone else to help? I mean, on and on and on. And it's rehearsed dozens of times. So this is all detailed out very specifically in how things work. And you are expected to follow the protocol. So like the president, and the many presidents who have met the Queen of England, and what we usually hear about in the news is how they screwed it up. How somebody came and touched the Queen on the shoulder. By the way, that's a no-no. You do not, thou shalt not touch the Queen. You do not touch the Queen. You don't stick out your hand to shake hands. So what's supposed to happen with the president, since they are never going to learn this stuff, is you have a specialist standing next to them telling them, nope, reach out. Now you may reach out your hand. And so they're quiet, but they're trying to coach the head of state. And then there's some presidents who just don't listen. Guess one. Did I hear it? Okay, good guess. Yeah, he's not the only one that didn't listen for that. So if you even Google like social gaffes made in protocol when president meets the Queen, you'll find like YouTube clips and things like that for it. So we talked about those protocols. So if you can't remember exactly what they are, just remember the Queen of England story, because those are protocols that are some of the most detailed in the world, because it's one of the longest lasting English-speaking empires. So, okay, we're going to use one where layering is a little better understood. You guys remember layering. So we're going to talk about a hierarchy. And this book uses an example of two people that need to communicate with each other. They're neighbors, Maria and Anne, but Maria speaks only Spanish and Anne only speaks English. So they both know sign language, so they're going to use that. Now, what's the problem with the author's suggestion that if you only speak Spanish and I only speak English, that we can use sign language to communicate with each other?
Sign language is not universal.
Correct. There's Mexican Sign Language and American Sign Language. Those are also different. So, it's not, sign language is not the same everywhere. Who knew, right? I knew because, yep, you knew, like you were the first person I've met that like totally killed it. Tech offers classes in Mexican Sign Language over the winter. Right? Yeah, so that's how I found out. As I saw, like, what? And so I asked some people, and they go, yeah, it's different. So maybe a better one would be like Esperanto. Have you guys heard of this? Universal language. So maybe they both learn that. So why don't they both just learn Spanish? Why would they not want to just do that?
Or learn a third language to be equal.
Yeah, so that's the idea. You learn a neutral language that, because you're going to end up speaking to other people that don't speak either English nor Spanish. They speak Russian or French or something else. Yes. So you can use Esperanto or some other third language to kind of equalize things. So this was one of the ideas behind TCP. When Vint Cerf and Bob Kahn sat down to write TCP, the predecessor protocol was something called NCP. And that's what the ARPANET ran early on the machines. And NCP was capable of connecting machines together that weren't made by the same manufacturer. And you could sit down and two different people could write the code and install it in their kernel and the operating system and communicate. In fact, the first two systems did so over a phone line between California and the East Coast. I want to say Boston. It's like what else would it be, right? It's like an obvious guess. Harvard, MIT, well, they're all there. You could probably guess California or Stanford for the Bay Area for the other one. But I think this one was from Los Angeles to Boston. And they were able to communicate with each other. The problem that Vint and Bob were trying to solve was they needed people to talk to each other where the speeds were different. So they were using different speeds of communication links. The manufacturers were different. The operating systems were different. and the size of the packets that they wanted to send to each other needed to be different, needed to change. So TCP handled all of that. It was the first protocol that got widely implemented that was able to handle the kind of diversity they imagined. So that's why everyone decided to, for the longest time, write translators to take whatever their language was, and they offered a converter to convert things into TCP. What lots of people did was they would take their packet and bury it inside of TCP, and then it would come back out the other end, and they would still be running the same networking protocol that they'd always run, like IPX or from Novell Networking or Apple Talk or something like that. It was never really truly TCP, but with the march of time, you know, it's like the Borg. You will be assimilated or destroyed, right? So everyone now speaks TCP natively. And when I saw IBM mainframe speaking TCP, I knew that was like, it's game over. It won. So that's what most people will use. Interestingly enough, there are some variations of TCP, very important ones that are emerging now. We may get a chance to look at some of them, but I'm not positive that we will. So I'm going to throw something up on, there we go, new transport. Oh, don't do that to me. Jerks. I saw it. I saw it. There we go, right there. Okay. So there's a working group in the IETF. You guys remember who they are. We saw the picture of all the fancy places they go to have conferences. That's how you remember them. And they are working on some areas of interest. And I don't know which file is the presentation, so I think it's probably just easier if I download it again. Let me see, did that do it? No. I need to do it this way. Okay, so they're looking at some interesting projects. There's a YouTube video for it as well. And here we go. So one of them is ultra-high availability, low-speed TCP, for example. There's some streaming things, M-Bone, things for IoT, basically. And I don't use the right names for it because I'm not working in any of these working groups. They're trying to make UDP more reliable, which is amazing that they're going to do that. They're trying to do multi-path TCP between wireless and wired. I mean, you have both networks, why not use both of them? There's been some problems solved already that we'll talk about this semester where the traditional routing protocols pick one route, period. It doesn't matter if you have 5 different paths to get from this router to this router across the internet. You know, you may have things that look like this. In this case, I have 3. You will pick, your routing algorithm will pick one. So here's the problem with that. You have 3 different people that each want to send a 50 megabyte stream of data to a user who's sitting on a network connection that only has 100 meg total. Let me draw it a little differently for you here. So 3 different connections arrive at a router, and this is a 100 megabit link, and each of them want to send 50. So this router also has other paths to send data, and maybe it has one more here to send data. It will pick one of these links, and it will send all the data. It's stupid. There's 150 meg. There's no 150 meg link here, but I have to point out to you what it does because without even coaching you, you would instantly see lots of ways of solving this problem. Like do the 100 here, do 50 here, do 50 in each, do 100 here, do the 50 here. You can get 150 meg across this. Traditional routing protocols will not do that. They will pick one link as the path to get from this IP address to the IP addresses for all the networks that are over on this side of the world. Yeah. tradition is the way we do it now, but it's simple. It's super simple. So they felt like the task of moving, changing routes constantly, trying to keep track of not just which is the best route, but which is the best route based on the total amount of bandwidth coming in, and then maybe you decide to let these people go this direction and these people to go this direction. That's too many extra routes. It was just not believed that those systems, which were very early, slow mini computers, could handle all of that. So it was extremely reliable to do it this way. It works. And as long as periodically you just throw more bandwidth at the problem, then you're okay. But that's been solved, right? So that's not a way you would want to design a network. And inside of an institution like Tech, we don't. We never would design a network like that. So this group comes up with workarounds. Sometimes it requires everybody to change the protocols that are running inside. And I need to catch up on this latest one for what they're working on. It would be lovely now that I'm sort of not having to work a day job like I was for the last 50 years of my life, that I actually go to one of these things now. I can actually do that. It's ironic, though, isn't it, that at the moment when I have the time, I no longer have the income to do it. So this is like when it's probably the reason why he doesn't talk to me anymore now that I think about it. But I had a friend in San Antonio, and he was bragging to me for his birthday not too long ago that he had bought this super expensive, high fidelity, like very elitist stereo system. And he had lots of records, phonograph records, so he bought this really expensive European turntable. They don't call it a record player. Once it costs more than about 10,000 pesos, you call it a turntable. That's what it's at. Right? So and he bought these super expensive speakers and all that, and I told him, isn't it ironic that at the time in life when you have the disposable income to buy it, the hairs in your ear have gotten hard enough where you can't hear the difference anymore. And he didn't think that was funny. So the IETF has working group presentations, so if you want to kind of catch up a little bit on what they've got going on, it's cool. You know, they've got a security area and a time area. One of the hot areas that I'm interested in is the IoT stuff, the Internet of Things areas. Okay, so that's getting back to kind of the layers and sort of the motivation for why we had TCP and what these problems were. They were trying to solve more or less this problem. So it's not that far off. So with face-to-face communication, they can deal with it. They can learn some middle language. Now, we had that inside of a computer. So you could write, for example, a program that knew how to read and display data from a database published by the federal government. The government used to mail CDs to you of agricultural data, the amount of harvest and the quality of the grain in every county, every month around the entire United States. So if you wanted to keep track of where was corn being grown and where was the earth producing the most corn and the best corn, the United States Department of Agriculture would sell you for almost nothing, $5 or something, a CD that you could buy every month from the United States Government Printing Office. They actually had bookstores. You could go and order it from them. And if you lived in a rural community, they would already have it. But then now what are you going to do to read it? So anyone could write a program that would know how to read records out of this database and display it. And that's an example of Anne and Maria figuring how to talk to each other on the same computer. The reason why TCP had to come around is now we separated those two apart from each other. Now the government says, well, there's another way to get access to the data. We have it online. And so if you can write your program to connect to us here, the rules you use for like asking for records and the way we formatted the data, the county is a number, it's 5 digits, it's at the beginning, etc. That's all still the same. So what you need now is a way to take a client-server communication that was happening on one computer and separate them apart from each other. A vast majority of early deployment of information on the internet was nothing more than that. Accessing data that had been already able to be accessed online on one computer and separating the two pieces apart. So there wasn't really any innovation in the information or availability or the kinds of things you could get, it maybe made it easier for people who didn't have it before, but there was no innovation in harnessing this to kind of radically change the way information was shared. HTML, HTTP did that, but there were predecessors to that as well. One very popular one was from the University of Michigan called Gopher. And you would go for information. Get it? Gopher is an animal, but it's right. So, and that's what you call somebody who is the one that always has to go and, like if you're the new person on the team and the programming team and they ask you to go to Starbucks and get coffee, you're the gopher. They call you that, right? So, because you're the one that gets to go for the stuff. All right, so that's the change. You could take that code and add TCP calls. This is why the socket library began as just a set of C language function calls. You pass it some parameters. So you would write a call, and in that you would put the destination that you're trying to reach. You'd put a port number, and then you'd put exactly the same data that you would have handed to that program running on top of the CD. Okay, so that's basically the motivation. I'm not going to go into as much detail as the book does, because this is not the first time you guys have seen layers. So what they try to do is to change things into the secret code and send it. So this implies security, which would be great, but the internet offers none. All the security protocols and mechanisms were added on by the application author. So the reason why, if you look in Wireshark for data to port 80 to most websites, you won't see it anymore is because they're not using it. Did you guys remember that? Did you see Wireshark in your class last semester? Everybody did? Did you search for traffic on port 80? Do you know what port 80 is for? Do you remember? I do not know what's going on with my eye, but it's getting worse and worse and worse. It's like driving me crazy. It's like I got stung by something. I don't know what's going on. So sorry, I may have to go rinse it out. I have no clue. So did you guys, so you don't remember what port 80 is for? Or you do? HTTP. So let's pull up Wireshark, and let's see if we can get it to run, first of all. And then what I'm going to do is start it running on my Ethernet port. And then I'm going to go to, like, well, let's just reload this page. Okay, that page is reloaded. I will stop. And we will come down here, and what I'm going to look for is stuff with, I don't want to do it that way. Let's go find some HTTP. So sorted it alphabetically by protocol name, and we'll come up here. So I have ARP. You guys probably remember that. I have DNS, loop, in. Where did the H's go? Why don't I see any HTTP packets here? They're not here. That's exactly right. If you don't see them, it's because they're not there. But wait, how did I load the web page without using HTTP? My browser absolutely spit out HTTP data. Where did it go? HTTPS is a signal that I want the browser to take the HTTP packet and pass it to another block of code. It used to be SSL, but more recently now, it's a protocol called TLS. You heard of it? So TLS is an encryption protocol. It's a block of code. You can install it in your operating system, and then everyone can use it, but the browser vendors basically, at the beginning, bolted it into their code. So if I know that this website will refuse a regular HTTP connection from me, and instead it's going to negotiate upgrading the connection to HTTPS, and it can do that right up front. And in fact, if my browser is going to try and guess that that's what it wants to do up front, then that's what we'll end up capturing. Now, that website, I don't know if I will see the TLS negotiation here because I'd already opened the page up and I'd never closed the browser window. But let's go down here and see. So what I want to do is find out what happened between these sites right before this did. So with that packet selected, I'm going to go back and revisit and look for a few more in here. So it looks like it had already negotiated this. So I'm here in any way. I'd have to go clean this thing up some more, but I'm not seeing TLS get renegotiated. So if you go to a brand new site, you will. You'll see it usually start off with TCP. You may see one or two HTTP packets, and then they'll disappear from then on. They'll go to TLS. So this diagram is not exactly accurate in implying that there is security when it says secret code. That certainly wasn't the case when he wrote the book, I don't believe. Okay, so ISO was established in the 40s, right after World War II, to try to set up some new rules to allow trade to emerge. There were a lot of countries in the world that had been devastated by World War II, and the United States was trying to, along with other developed nations, enhance lots and lots of trade. So standards helped do a lot of that, especially in areas where countries like the United States wanted to manufacture products that were needed to kind of rebuild countries. So the model they came up with was much later than that. It was the OSI model. It's unfortunate that it's the reverse of ISO. If you ever develop a standards organization and a protocol, please do not make them mirror images of each other, okay? You just promise me that now. I will have accomplished something important for humanity if you'll do that. Okay, so this is like a source of constant confusion. So what we'll look at is the idea. The difference between TCP and the ISO model are the two layers in black. It doesn't mean that TCP doesn't do these things. It just means that they didn't bother splitting them out as separate coding efforts with separate function calls and separate definitions of the data that's going to be passed up and down. They put it all into the transport layer, basically. So the transport layer is a little difficult to figure everything out because TCP and UDP live there. They're very different from each other, but they're all crammed in together because nobody bothered separating them out. Also, the act of negotiating, handshaking with another site, the three-way TCP handshake that you know about, that should have been put into the session layer, but it wasn't. And then finally deciding how you want to negotiate the data, the language, the size of the packets, all that. That's something that a presentation layer would very often worry about. There are other protocols, and they're used. TCP isn't the only protocol that gets used. It's the dominant one, but it's not the only one. So you may not really have to worry very much about many others, because even in the presence of other protocols, at the end of the day, they're usually transmitting TCP down inside. So they may use it just to carry a hidden TCP packet. Okay, so you guys remember some of these layers are implemented in software only in the end systems, the things that hang off of the end of the network. Think of it like what hangs off of a tree, the fruit. It's only at the edge of the tree. It can be lots of places, but it's never grown on the trunk or in a branch. It's the terminal point of a path for a tree, correct? So it doesn't really matter to the internet whether it's a server in a big Google data center or a cell phone or a laptop that you're dialing up with at home. Those are all the same to the internet. They're all end systems, otherwise known as hosts. So hosts are the only ones that implement these higher layers. And in the core of the network, even in OSI, which is what we're looking at, the only layers that are implemented in here are the bottom three. So are there exceptions to that? Do routers actually have code that will communicate with you at the application layer or at the transport layer, for example? Use the internet as an example. So let me ask you a question. You're a network manager for tech. You have 35 campuses. You have routers at every one of them. Some of the sites are big and have lots of routers. Some of them are small and maybe have a few. and one of the routers is acting odd. So you want to find out what's going on. What will you do? How will you find out what's going on? You can make up an answer. If you knew all the stuff I'm asking you, you wouldn't need to come to this class, right? So don't feel bad if you don't know the answer. But guess, what do you think network managers do if they want to find out what's going on? Yeah, so do routers have passwords? Sure. So you guys have connected to other computers before. It's a Unix system. So how do you log into a remote Unix system? And what app would it be? Like if I opened up my command window, yeah, so you find out the IP address. So what command do I want to type here if I want to log into another Unix system? Secure shell is one. That certainly will work. What about telnet? You guys heard of that one before? Telnet's an interesting one we'll come back to.
But it is deactivated.
In most. So you can turn it on if you want, but you're right, it's not widely available in lots of systems. But that's not because it doesn't work or not good, because it's easier to develop something more secure than to get everybody to patch telnet. But in either case, whichever one those are, the fact that I can, from a command prompt, as just a little old end user, open up a window and I can do something like that, what category of software am I running? You said it a minute ago. It's an app. It's running at the application layer. So if I'm running an application protocol, telnet is absolutely an application layer protocol. You can look up the RFC if you want. What must be running in the router to answer that connection? Look at the picture. It has to be. These things aren't ever diagonal lines. They're only horizontal. So if I'm able to open a telnet connection to the router, it absolutely has to be running an application layer protocol. And they all do. Your other alternative is to drive to wherever the router is and plug your laptop into the console port and manage it that way. Who wants to do that? Unless the network is down. So we used to, in the old days, and there's different ways of doing it now with cellular, we used to have to buy a phone line every time we installed a router and find out the phone number and put a modem in it and buy this device from a company called Black Box. What a great name for a company. They built all kinds of weird devices to do exactly these kinds of things. You plug a phone line into one side and a serial cable into the other. It'll plug into your router, and you call it up. It will answer the phone and connect you to the router, just as if you were there. But it will implement a password, so you have to type in a password first. That was the extra thing that it did that kept anybody else from calling it up. So we used to buy these things and put them in because otherwise you'd have to get on a plane and fly to wherever the router was to get in and manage it. So anytime you want to manage a router, or let's say you want to just download a new version of the software, or you just want to ping the router. Ping is something I can run from a command prompt, right? Therefore, it's probably a application layer protocol. Now, ping is tricky, so we'll talk more about it later in the semester. You can get away with ping without having to run an application layer protocol, because what ping really does on your computer is it makes an operating system call to ICMP, which is a layer of software running alongside IP at layer 3. And the message actually travels there. Well, what do you know? Routers already have layer 3. So there are some exceptions, but mostly 99% of software you run will be application layer software. So if I ever ask you a question about what layer something's running at and you don't absolutely know the answer, always guess application layer. Okay? You heard it here first. Always guess application layer. You'll almost always be right. So does anybody know what layer TLS runs at? It's a good guess. All right, what about SSH? And on and on. SMTP? For email, yeah, good guess. So HTTP, FTP, UDP, well, UDP doesn't, but FTP, all these things run, TFTP, they all run at application layer. So sometimes there's tricks, but ping technically is an application. It just cheats because it's not a network application. It doesn't make the call to a remote site. It makes a call to ICMP. That does not make it a network application. ICMP builds its own packet and sends it. It doesn't have to use the same process. So we'll talk more about that this semester in detail as well. So everything's horizontal. If anybody, do you ever have the urge to draw like this? I'm going to come by and do that. No, always horizontal. That's why we have layers. So the baggage claim handler at the airport may not talk to air traffic control. The person selling the tickets does not need to talk to the captain of the plane. They, all done in layers. The only time you talk to another layer is within a system. And you may talk one layer up and one layer down, and that is it. So that's what these black areas are in between these layers. So layer 7 can pass something down to a lower layer, and it can receive something from a lower layer within this system. For the application layer to receive something from a lower layer in another computer, you'd have to draw a diagonal line, and I will come by and slap your hand if you do that. You may not draw a diagonal line. It must be horizontal, okay? So in this class, the earth is flat. Everything is like that. And the same in routers. You'll notice routers pass things around. So if you get stuck and you're not really sure what path a packet will take to get from one host on one end of the internet to another, and you're just having a hard time sort of figuring it out, whoops, just remember the diagonal line speech I gave you, and you can grab yourself a red marker like I'm getting ready to do here and get something thick, and you can say, well, if I'm trying to get from here to here, the only thing I'm allowed to talk to within a system is a layer above or below. So the only path I have is this path. And I have to get to the network layer to check the next IP address of the next router. And so, there's now some logic behind why they get drawn like that. Have you seen a diagram like that before? Where the line goes out of one system and goes up into the next, etc.? Some of you, yes, some of you, no, it looks like. Okay. Okay. Do you remember encapsulation really well? Sort of well. I'm getting some, so when you nod your head, but it's got a little bit of the side to side like that, that says sort of to me. When you look at me and you go like that, that's definitely a maybe. So we'll go over a little bit. So the way to think about encapsulation is, I have a birthday card I want to send to, yes? I have a birthday card I want to send to Mario de la Fuente Martinez. Used to be the department chairman here. He's now the regional dean in Guadalajara. So he's got a bunch of campuses, and he's responsible for networking and some other stuff. So I want to send him a birthday card. So I drop it in the box for Olga, the department secretary, next to Armandina. Do you guys know Olga? She's the one that makes the place work. Bosses come and go, but a good secretary is worth their weight in gold. For most large companies I've ever worked with, most of my clients and my customers, the CEOs usually don't last all that long. The ones that really know how to do everything and train the new one is the executive secretary. So I used to, and I use lots of stories that hopefully will help you in your career. I used to have cards for different outfits and different companies, and I would write down, every time I went to visit a customer, I would write down what I wore that day, tie, shirt, and suit, to make sure that the next time I went, I wore something different. You show up wearing the same thing twice, and you're going to get noticed. By whom? By the secretary. What's the secretary going to think? Are they going to be impressed? No, they're going to think you're a used car salesman. And so you need the secretary to be on your side, because if you need to get a meeting with an executive, they never have time open. It's always a survival of the fittest. The only way you ever get a meeting with an executive is if you are more important than someone else on their calendar already and they get pushed off and you replace them. That is the only way it ever works in your whole career. They will never have open time. So you better have something compelling if you want to talk to them, and you're going to need the secretary's help to make it happen. So if you go in and you notice things, like make note of the pictures of the family, don't wear the same thing twice, be very polite, always say hello to them first, wait for them to get off the phone, doesn't matter, make the boss wait if you have to, and if they drag you in, at least wave or something, and that will set you apart from 99% of other people that try to get into those offices. They'll never make it, right? It matters, because what they're not getting is the pay. So if you can't get the pay, at least get the respect. I had a boss once that told me you can have fame or fortune. Pick one. You can't have both. So usually true. Okay, so back to kind of what we're talking about here. With encapsulation, I want to mail Mario a birthday card. So I go by Olga, I ask her to do it. So I've written just Mario on the outside of the envelope. She will take it and put it in an inner office envelope, one of those brown things that ties up with a string that have holes in them that you've seen. And it's an envelope you can use 100 times. It's got lines all the way down it. And every time you use it, you mark off the one above. And it goes to the mail room on campus. They will put it into a bag with all the other envelopes that day. And it will go to DHL. They will put it in a big truck going to DFA or straight to Guadalajara, and it will go in a plane and container. All of that is encapsulating. Somewhere buried down inside there is my birthday card that I bought. So the person at each layer, at each stage of shipping this package, the person at the airport doesn't care who the birthday card's for. They don't even care that there's a birthday card. The only thing they worry about is the address they see at their layer. This container goes on this flight for Aeromexico or for DHL to Guadalajara tonight. That's all they need to worry about. Okay? And they may tell the layer above that it's loaded. They may take bags from the layer below to put them in the container, but that's it. And it gets unwrapped on its way as it gets closer and closer. Mario gets it. He doesn't have to know any of those details. That it got there via DHL, that it was in this size of envelope, big sack, that it was in a box, that it was in a brown envelope, because his secretary undoes that last little part. So that's encapsulation. The other example I can give you that'll stick is from a grocery store. If you buy a box of cereal and you get it at home, the cereal grains are in a bag, that are in a box, that are in a grocery bag, that are in your trunk, that are in your car. You drive it home and you undo. All that is encapsulation. Right? So if mom mails you a gift box at Tech with that stuff in it, it just adds another couple of layers of encapsulation. So that's basically the idea. What you'll notice at the bottom is true with the TCP/IP model as well as the OSI model. What's true at the bottom is for some layers, you have information you add not just at one end, but at both ends. The only thing I would change about this diagram is we are always used to seeing the header on the left, correct? In all of our TCP training we've had, in most books you will. He put the header on the right because he's showing the packet is being transmitted from the left-hand computer to the right-hand computer, and the header is the first set of bits to enter the wire. That's really important for routing, and we'll talk about that later in the semester as well. So these bits go in first, then these bits, then these, and these, and these, and these, and finally, there's the birthday card. And after all this is done, you can have not just a header, but a trailer at the end. And usually there's one layer that adds a trailer. And sometimes you can optionally get rid of them as well. So the physical layer is responsible for bits, one node to the next. The perturbation of the sinusoidal pattern that otherwise would be a nice simple sine wave, and you and I come up with some scheme that we're going to use to transmit over that sine wave. So you're going to build some electronics that are going to change the shape of that sine wave, and I'll know what that means when you do that. So you'll take what would normally be called just a carrier. You will listen to see if the carrier is on the network. If you hear that sine wave, you know it's available. If you see perturbations on it already, you may conclude that it's busy and wait. But if it looks like this, then it's available and you can transmit. And so your electronics will change the voltages as this is going by, and I will know what that means. That's basically what the physical layer is responsible for. The physical layer will usually not bother retransmitting anything. It will usually tell you if it sensed a collision, because at the same time it's generating the signal, it's also continuing to listen and observe the pattern that is on the wire. And because these are electrically conductive cables, or in the case of fiber, they're not, of course, but with everything else, there's an energy that you can get out of it. Any interference that happens presents itself as further perturbation of this sine pattern. So if you think you're issuing this pattern on the wire, but what you hear is, this one, you may say close enough. And you may be willing to tolerate that. If what you hear looks like this, you know something has gone wrong. So you've added energy to this pattern. You've caused the electrons to begin propagating a certain pattern across the wire. Nothing can make that stop. So when there's a collision of packets, it's not as if like a collision of cars where it like stops or whatever. The electrons don't explode. You don't have a fusion reaction that ends the planet. Right? So the charge is still there. The only thing that's going to happen is it's going to be interfered with. It's exactly like a wave in a pool. If you're making a pattern by throwing a rock in the center of a pond, and it's propagating its way out, and somebody else throws another rock in the pond, they just combine. The rocks don't explode. So just forget collision implying anything like collision. It's just combining signals. And the new signal will propagate left and right just like the old one was going to propagate as well. So you will be able to hear it. It may take a little while for it to reach you, but it will eventually reach you. This is why you have to continue to listen to a cable after you've transmitted what the user asked you to transmit. That's why there's a minimum packet size for things like Ethernet. Even if they only gave you 1 byte to send, and you have a header that's really small, 48 bytes on top of it, you've got to continue to transmit zeros for the payload, whatever that looks like on your wire, for a certain minimum amount of time to allow any interference that may have occurred at the far end of the network to have a chance to reach you, so that you can hear for yourself that your signal probably never made it to all of the possible destinations on the cable. And that's when you conclude there's been a collision, right? That also implies there's a maximum cable length. So they're connected to each other. Maximum cable length infers minimum packet size. If you need your packet to be smaller, then the cable can't be as long. Does that make sense? Because you're going to stop listening sooner if the packet is smaller. So if you need to be guaranteed that you're going to see a collision happen, then it can't happen that far away from you, because it takes time for the electrons to get there. It's near the speed of light, but it's not instant. Right? So we'll see diagrams of that. We'll look at more examples of that this semester as well. But you will understand that completely by the end of the class, right? By the end of the semester. And I will tell you, and I don't think there's a single, I mean, this is such a generalization. I just hope I'm wrong, and I'm certain I'm wrong, but I'm going to say it anyway, because my belief is there's not a single person in the faculty at the other school where I teach that knows this in that amount of detail. But I'm already thinking of some exceptions of where people have the right background, so it's probably wrong. My point is, it's very unusual for a computer scientist to know really what the hell's going on the wire. It's just like magic or something. Well, it isn't magic. And you do need to know about it, and it affects the protocols you develop, and it affects the programs that you write. So you can write programs and ignore it all day long, but if you want to write a really good program that does a great job, and you want yours to perform better than everybody else's, then you should definitely pay attention to it. So I'm getting like super dry. Oh, here's my bottle of water. Couldn't find it. I came prepared. 2 cans of Coke Zero and a bottle of water. So don't know what happened today. Apparently I ate something salty. Must have been lunch. Okay, so we will understand what's going on. Ethernet is not helping the situation with us very much because Ethernet combines the physical layer and the data link layer into one. So we usually don't ever worry about the physical layer. But when you get into Wi-Fi and things don't work so well, this will pay off in understanding. So we will look at some Wi-Fi simulators this semester, and we'll see sort of what happens with signals and interference when there's multiple people that can hear it at the same time. And those are kind of fun. So the physical layer moves the bits one to the next. Data link organizes them into frames. The network moves those frames from source to destination. They add a logical network address. So I can give that address to whomever I want. It's just like the address on a house versus the identity of the person inside the house. I can change who's inside of an apartment one semester to the next, and they can all still use the same address on the outside. Right? So you've got multiple layers of addressing going on. I can have different people drive my car. The placas will always be the same, but the licencia de conducir will have a different number every time, right? Perfectly fine. Same seat number, same plane number, different flight number. The same plane will change flight numbers during the day as it moves from different destinations. But the call letters, the painted on the wing, all of Mexico start with X, for example. You ever seen those on the side of a plane? Wonder what they are? They're like the call signs. Those don't change for a plane. Okay, enough on that for the moment. So TCP was well before the OSI model, and they don't match exactly. I'm sure that Bob Kahn and Vint Cerf spent time trying to figure out how many layers was too many and enough. They had a little bit of work before them to guide them, but when you're small like that and you're trying to figure something out, probably the most important factor to you at the time is how many people can we get to help us and how much of this do they know? Well, I know about writing the software on the computer, but I don't know very much like you do about encoding bits on the physical layer. Okay, we'll make those separate layers then. You deal with that one, I'll deal with this one. And they kind of took it from there. Well, who's willing to write the code for this? Well, this guy is, but he's in Boston. He can't fly out here every week. So let's just split that off as a layer and give that to him. So they're probably just common sense reasons like that figures out. So here are the two layers side by. This is not those two layers. That's coming up next. This is two versions of TCP/IP. Sometimes people will leave off the physical layer when they draw it because there's no addressing. There's no numbering scheme. We don't number the bits, for example. And after all, what's connecting the physical interface of one device to the physical interface of the other device is a point-to-point dedicated circuit. Okay? A point-to-point dedicated circuit. If you are passing something off, you can't get around that. There's no way to avoid it. Let's say you've got a network. I don't like this color. Let's say you've got a network sitting at the edge of tech, and tech's got lots of devices out here, and you want to get traffic to telnets, telmexes. See, I'm saying telnet when what am I doing? To telmex's internet service. Telmex runs an ISP. At home, you can buy internet service, for example, from Infinitum, for example. And what that has is a bunch of routers, and they don't charge you for this circuit. That's not the way they sell the service to you. How does Telmex charge you for internet service? By bandwidth, right? So bandwidth basically means the number of bits per second you can send over the wire. Do you really know what this technology is? Did anybody ever watch them as they've installed it? You know, I won't even pass. I drive people that I walk dogs with and stuff crazy. Yesterday is a perfect example because I stopped this guy who was painting location marks on the street and interviewed him on my cell phone for class. And he's like, "You're videotaping this?" I'm like, "Relax, it's for the children." So he's like looking at me like I'm crazy. Okay, that's fine if you want to call me that. But, you know, I'll stop and look and examine what people are doing with the outside plant because that was my career for a long time. So they use fiber, and I bought a 50 megabit per second package. Can fiber do more? Well, let me ask you this. If I call Telmex up and say, I should have bought 100 instead, do they have to come and reinstall new cabling and everything? What do? They like log in, punch a couple of buttons, and presto. So 50 megabits is not the capability of this circuit. What they're doing is taking my packets and rate limiting, sending setup messages back and forth. There may be something in their device here that will just not send more than 50 million bits a second, won't even try. There's certainly something in their bigger router at their building that will take all my incoming packets and put them in a queue that will not drain faster than 50 megabits per second. So one way or the other, they have policing that. And so I am buying a data service. I'm buying a switch service. The only thing I ever send out of my computer are packets to them. But like it or not, this is still a point-to-point dedicated circuit. It runs from me to some other piece of equipment, and I'm the only one on it. There's no way to avoid that. So all these connections always look like that, even if it's not the way you're buying it. So you can't get away from having to worry about the encoding at some layer or another. Okay, the presentation and session, TCP handles some of this stuff, but sometimes you'll build this into your application layer as well. You can if you want. So an example of building the presentation layer into an application would be when HTTP negotiates what language would you like me to give you the web page in. And if you guys remember looking at HTTP packets with Wireshark, there is a keyword value pair in the very first message about the language that you can handle. So that's something that you might negotiate inside your own program because we don't have that layer in TCP. Before I gave you examples of how there are some things in TCP that seem like session and presentation layers like handshaking, for example. Okay, so let's walk across a school network with 4 routers and a bunch of switches. The switches are the boxes. Do you guys remember the difference between routers and switches? One starts with an R, the other starts with an S. That's one difference. Yeah, so the model that we teach you to kind of keep them separate is that switches don't have layer 3. Routers do. The idea is that layer 3 is kind of diving off the deep end. It's really hard. It's very difficult to program routers manually and to have your network run efficiently. It's just constant problems because networks change, and every time they do, you got to do something to the router. So that's why it takes a very highly trained systems engineer that's got lots of Cisco certifications or whomever, and to really have the responsibility for routers. Switches, on the other hand, we teach you that they only go up to layer 2, and they're simple, they cost less, they maybe don't even have to be programmed at all. The reality is much more gray than that. All switches handle layer 3 types of tasks. All routers handle layer 2 types of tasks as well, because they have to. We can't afford to just constantly separate, and it's needless to do so. So we'll have examples of why that is. If I can show you one really specific fun thing I did with the switch if you'd like to see. Let me think of, let me see, here we go. There's the folder. Sometimes I show this to the beginning class, but there's only one person who may have taken that from me, I think, this semester, so we're probably okay with this. Let me just take a quick peek and make sure these are all what I want. Yeah. So this is a series of photographs I made at a conference called Cisco Live in Cancun 3 or 4 years ago. And it was a trade show for customers, and they couldn't figure out why every year there's more and more customers who come to Cisco Live for Latin America from like Europe and Canada. I'm like, really? It's like in December. Why do you think they're coming to Cancun in December? From London or Berlin, for example. Because it's like minus 1,000 degrees there. So it's freezing cold. And they get to come here and eat Mexican food and drink tequilas, and there's a beach, and count it as a trade show. I mean, come on, guys. So you should be marketing to these people. So more and more, there's like these people that show up. And so we have all of our gear there and everything. And this was a switch called a Nexus switch. It's a $250,000 switch. Yeah. And that's a small one. There's $1 million versions of this switch. And people buy boatloads of them. So, because it runs cores, pieces of massive data centers, for example. So this one is a Nexus 7702. It's kind of a badass machine, but it's a computer. Basically, it just has very specialized high-speed switching, and it's a 2-slot. So you see all this stuff in here. These are all radiators, basically to dissipate heat, because there's chips underneath each of these things, and they all are very hot. So the chips won't melt from getting hot, maybe, but everything else around them will. So you kind of want to get it out of there. So I have, here's a much better one of it. You can see there's a battery here, like there is in almost everything, to keep the clock going if it loses AC power while it's being shipped, etc. There's some memory strips here, just like the ones that you'd put in a laptop, but just a different variety. That's all. And so this thing was sitting just like this, I mean, with the cards out and stuff. And so, I thought it was like a demo. I'm like an engineer, like I take stuff apart. That's what you're supposed to do, right? I mean, anybody here never opened their computer? Really? So here it is, and these little things, if you remove these clips, you can pull the heat shield off. So, like, why not? It's not running or anything like that. So I'm looking at the side and, proving that Foxconn really does make everything on Earth. And they make all of Cisco stuff. There's a $4 billion plant in Guadalajara, in fact, making Cisco stuff. And, I'm pretty impressed that I was able to at least get the picture to take. So here's one of the SIM strips, so you can look up these part numbers and figure out what kind of crazy stuff we're doing. It's probably faster than what you've got. And then here's a Cisco custom chip. And you see this kind of gray stuff around here? Anybody know what that is? The gray junk? It's thermally conductive adhesive that was being used to hold the heatsink on that I pulled off. Right, so pulled it off, and here's what the heatsink looked like. So underneath it's kind of a small chip, and I pulled some other ones off. It's my first time ever to really get close and in touch with one of these, and it was after the rest of the stuff that I'd heard of some of these suppliers and vendors before. This is a crystal, I want to say. I believe that's what I decided this one was when I went and looked at it. But things went well. I put the heatsink back on, and I during the week took a bunch of other stuff apart on it to show customers and things like that. Everything was great. About a week and a half or 2 weeks after the show, there's this blast email message that goes out to everyone that was involved in the show. Who the hell was the moron that took apart my Cisco 7702 from my lab? And I'm like, and so the guy I was working with in the lab, he goes, don't worry, your secret's safe with me. And I'm like, I owe you one, man. It's like, that's what he gets for leaving it out next to me. You should have known better. Take it apart and leave the pieces out there. I'll do it again next time. Bet next time they do something different, and they did. They started putting them under plastic, clear plastic boxes, so you couldn't get to them. And I'm like, it's your fault for, like, first of all, trusting you could ship a $250,000 switch into Mexico through the postal or however you did it, or you could get it through customs. And I never get anything through customs. Like last year or 2 years ago, I brought a bunch of Beagle board kit boxes. They're like Arduinos or Raspberry Pis or whatever. They found them. They go like, what's in the box? And I'm like, 78 of these things. And he goes, you need to go talk to the officer. So 33,000 pesos later, and I have a permit to bring them into the country. So, and I'm like, who's going to pay for that? So to scratch out a check for that on the spot. So, you know, in my defense. And I'll show you some other fun stuff that happens in the industry as well. If you do go to a trade show, particularly if it's ever a Cisco one, ask them if they can show you like what's under the heatsink. See if you can talk them into pulling the thing off. So in our case, we've got switches, could be Nexus, probably not. You have routers in here as well. And we've got an imaginary internet. So we're going to use this model to kind of walk through the rest of this section to figure out exactly what's happening layer by layer as we get things through here. So the physical layer deals with the media. We've gone over almost all of this already, so we don't need to spend much time. The important thing you got to realize is if you have a physical, dedicated point-to-point circuit connecting devices, there's exactly two, one on each end. Each one of them has to have electronics attached that knows how to perturb that sine signal and also knows how to interpret it. It's a piece of electronics. It must be present on both ends of that circuit. And the sine wave you're sending there has nothing to do with whatever sine wave may or may not exist on any other wire on the planet. Agreed? It's a separate piece of wire. You've done something to those electrons and those molecules that's not being done. It's only affecting what's in that wire. So the reason why I give you that detail is because lots of people get lost on what's about to happen next. So if I've got links here, 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 and let me copy this so I can draw on a little bit here. So the point of that is if I've got these links, and I'll switch to a different color. Here's a physical link. Here's another one. And the diagram, when we go back to it in a minute, it's going to ignore the switches. But for a minute, we're not going to ignore them. So how do I know, what do I mean that these are separate links? Well, they're separate Ethernet cables, for one thing. Let's assume these are all Ethernet cables. They're sitting inside of our lab. This cable is different than this cable, right? You don't run the cable through the guts of the switch and open it up and pass it through and somehow tap into it. No, it's a separate cable. So there has to be separate electronic circuitry on each end that is changing what your sine wave looks like, and one at the other end that knows how to interpret it. So how many implementations of the physical layer in hardware, probably, software is not fast enough, in hardware are there on this diagram? So instead of counting it up, tell me the formula. How are you doing it? So you go to eBay and you buy Foxconn made or Broadcom made or Intel made implementations of Ethernet on a chip. Most of the time you'll buy them from Broadcom. They sell what's called merchant silicon. They've implemented a protocol in a small chip and anyone can buy it. So it's not custom, it's merchant. So you can find merchant, and in fact, if I look for merchant silicon, that's a guy's name. I don't know if I found it. Let me do this way. Here we go. Here's a Broadcom data sheet on Ethernet on a chip. So you can buy this and install it on your Ethernet card or burn it into your motherboard, and you can look up to see whose Ethernet chip does Apple use on the Mac Pro, whatever model. They don't make their own. Everyone buys Ethernet from someone else. Why not? It's problem solved. You don't need to do it. So how many of those chips, if I opened up every piece necessary on this diagram, and everyone was using that chip, how many of those chips would I find? That's what I mean when I ask you how many implementations are there of the physical layer code in firmware, because software is not capable of generating sine waves like that. How many chips would I find? 12, I hear. Anybody got a different answer than that? 8? What if I told you it's 26? Why? Exactly the formula I'm looking for. 2 for each cable. 1 on each end. You got to have a sender and a receiver for each end. So what happens on this cable gets generated by the chip here and gets received by the chip here. And that's the end of it. I told you people got lost on this stuff. Didn't I tell you? So this is, for some reason, hard for all of us, for all computer scientists universally. I don't know why. It was hard for me, too. That's because I'm not very smart. But this one is, you know, it's a brain teaser. Right? So there's a chip on each end of this thing. Whatever gets generated here has nothing to do electrically with what happened here. After all, this could be Wi-Fi, this could be Ethernet, this could be fiber. They're not going to change the sine waves the same way as each other. They're not going to be generating patterns. They use different encoding algorithms to get things encoded. All right, so back over to the diagram. That's, like I said, we'll pay attention to the switches for a minute, but the book ignores them. Yes? Did I count one too many? That's certainly possible. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, you're right. It's just 24. Right. There's 2 extras hidden inside of here. I'm kidding. Yeah. No, there's. Well, you forgot to count this random line here and this random line here. Yes. Yeah. Thank you. So there's only 12, but the book is a little different than that. The book ignores the switch. And so the book basically implies that the switch is so transparent that it's probably using exactly the same technology on both sides. So the electrical signal that you see here should match the one here. That's not true. But it's okay for purposes of understanding kind of at layer 2 what's going on. Maybe you could get away with it there. But even there, it's not exactly true. Yes? Good question. It depends on the technology. For Ethernet, you've got 8 wires, so you're not sending both directions at the same time, but you can. If you've got the electronics capable of detecting signals in both ways, it's much harder. So most technologies separate the two from each other. Fiber almost always separates. In fact, I don't know that I remember ever using one in practice that didn't. So for airwaves, for radio waves, you don't get that luxury. It's, you know, it's a little bit different than that. But that's basically the idea. But with telephony is bidirectional, and there's only 2 wires. So that's proof that you can encode things, you know, in 2 directions at the same time. You can't understand each other because you'd be talking at the same time. So they let the fact that we are not good at doing things in both directions to make it easier on the network, not having to worry about it. Computers would love to send things at the same time, but you and I, it's rude, among other things. Right? So there's another example of where human factor psychology, and somebody had to look, Is this true all over the world? Do people not talk over each other in any language? Can people understand somebody else, maybe a snippet? Turns out nobody likes to do that. So we don't need to build our network to always handle bidirectional communication. And when they built communications for things like the lunar module, to go up to the moon, they had a little protocol they added to it because there's now latency delay, and they would make a beep tone every time you let go of the transmit button. You remember back to those days? Anybody know what I'm talking about? So you want to hear it? All right. A little fun. Let's see if we can find it. Let's see if we can hear a little bit of it. Hopefully this has not been edited. Oh, no, I didn't want to click that. Okay, let's see. I have no idea what this crazy thing is here. Okay, hear that beep?
Oh boy, it's really something that was fantastic here. You couldn't even imagine this. Roger.
Hear the
We
beep?
know about that. Could you go the other way? Go back the other way.
That's bullshit. That's not even English, American English. That's so accented. That did not come from Houston. I worked in that building, Building 33, for years, so that no one spoke like that in that building. You know, this is like some fake thing about talking about UFOs. If they're going to try and put one over on you, they need to get somebody with exactly the right Texas area American accent. That is not right. Okay, but you heard the beeps. So what was happening there was there's latency. So that network was designed to only send things in one direction at a time. So you needed to know when it was your turn to talk. So when they let go of the microphone button, they're telling you they're done talking. It'll make an audible beep so you know it's your turn to tap your microphone down if you have something to say. Make sense? Well, like a walkie-talkie. Yeah, but it's not like one person or the other is always transmitting. You only transmit when you push the button and you stop and signal the other person you've stopped when the beep happens. So it's interesting. It's a little more complicated. It's a protocol. Somebody had to actually write a protocol about it. Okay, so in this case, it shows that at each step, the task is to get bits from one side to the other. So one way to draw this up at the top, if you drew it a little more formally, would be to show a set of links as the path that the routers chose. They chose, in this example, to use links 1, 3, 5, and 6, and ignore these other links over here. That's just an example. Could have gone another way. And source and destination is shown with open dots or filled in dots. Okay, so we'll speed up from here on out because some of the highest level layer stuff you know about. And that stuff's not confusing to people like some of the low level stuff is. Let's take a 15-minute break, come back, we'll spend at most an hour and get out of here a little early. I don't think we have enough. Sound good? All right, so it's 7:30 exactly. 7:45 we'll come back. And in the meantime, somebody's going to have to coach me on, like, do you guys always say 21:35 or 17:35 or 7:25? Do we use the 24 or the 12-hour clock? I mean, that's like, some stuff uses 24. Yes, even in emails and things, like online systems at tech and stuff. So I guess that's just to be super. Okay. So I'm okay saying 7:40. Okay. Okay, so the data link does try to send things error-free between the two connections. So it will listen for collisions. It will complain if there's a collision. But usually the task of resending the bits, let's say you had an Ethernet frame that represents 512 bits, and you start handing the bits down to the physical layer, and it detects at bit number 100 a collision, and it lets you know immediately. So it goes through this crazy pattern of blasting out an unmistakable signal that ensures that no one mistakes what's happened as a valid signal, to make sure everyone understands, as you do, that it's a corrupted packet. So you'll usually, blast out something loud to let everybody. It's just like when somebody cusses on the radio. I don't know if they do this in Mexico, but they'll beep you. Do you guys know about that? Do they do that here? Yeah. Not with music on radio, they don't. They play every freaking word that's in there. I couldn't believe the first one. Yeah, no, they don't play the clean version of English songs here, that's for sure. So but in the US they even beep out the bad Spanish words. And I'm like, all you're doing is teaching me Spanish. Because now I go to the song and I look for exactly that word, and I go look up, okay, what other meaning does that word have? Because that's not a bad with a normal meaning. Oh, yeah. So, that's the stuff they don't teach you in Spanish class. So beeping out is broadcasting an undeniable signal that it's corrupted, and most data link systems will do something like that. So let's say again, 512 bits in an Ethernet frame. You start to transmit the bits. The physical layer detects a collision. It lets you know there's a collision. It takes care of making sure everybody knows. Now what? With Ethernet, it wants to resend the frame. So it holds on, layer 2 holds on to the bits, and layer 1 is asked to resend them again. So it's layer 2's responsibility to keep more than the current bit being sent, or whatever's being transmitted at the moment. So there is typically ways of dividing up the streams of bits. You have to have, as one of your encoding decisions, some way of dealing with it. So a lot of this stuff is moved up a layer from physical, because now on this slide we're at the data link layer. So error-free delivery, so that explains how that works with the physical layer. You typically have addressing now. So this little chip that you bought that's going to do the encoding for you, you're going to give it a number, a serial number, an Ethernet address. And you put that in, not the manufacturer of the device, not the manufacturer of the chip typically, but the manufacturer of that system. They can assign whatever they want. Some systems will let you reassign, change the MAC address. You can look it up, Google, see if yours will. Depends on the type of system. And that's dangerous sometimes, but also extremely helpful sometimes. So it's very, very useful in network security. If somebody's trying to hack you by your address, just change their address and change some other system to the bad one, and just collect the packets that do nothing anymore. So there's fun. Sometimes of the network sniffer, you will tell the network card, I want you to give me copies of only packets with these hardware addresses. So you'll see all of them go by, just hand me copies of those. So that's kind of like giving you that address. They will usually implement a way of beginning and ending a frame, special patterns of ones and zeros. For example, at the beginning of Ethernet, you have 101, and then your Ethernet frame starts. Most people eliminate all that. They use a very short header instead of that one. There's a reason why it's that long, but it's not needed so much anymore. So that's basically framing. Flow control is something you do to make sure that you're not going to send more than the receiver can handle at a time. This is totally different than buffers and routers dropping packets and denial of service attacks and all of that stuff. This is at the physical data link layer. You want to make sure the other side is ready to handle what you're sending. You need to be able to detect and retransmit frames that didn't make it for whatever reason. And if it's a multi-device link like Wi-Fi, as we'll learn, you've got to figure out how do you know when it's your turn to talk. There's lots of different schemes of doing it. The early ones included things like, I will come and ask you if you have anything to say. Wait until I come and ask you. You do not get to tell me you want to talk. I will watch for you. I will come to you and ask if you have anything. It's like the postman. I'll come by when it's time for me to come by. There's no raising your hand. All right, makes sense? Same thing in TCP/IP. One of the things that's unusual, that's not universal, is in Ethernet frames or in most data link layers, it specifies that the source and destination are both there together. Why do you have a source address in a data link layer? Well, there's reasons. The book goes into that in a little bit of detail. But there's some reasons to specify. If you want to validate who's sending something, only accept traffic from certain people, make sure that it is sensible, and it also really helps the switches in the middle learn where you are. If every time you send a frame, you put who you are in it, then they know where you are, right? So this is how switches learn what's on the network. They don't learn by the destination address, and let me draw it out for you. This is one of the reasons why switches are popular. Let's say I have user, let's switch to something that's not a first grade crayon. Okay, let's say you have user A sitting here, and you have a switch. You have B here, C, and D. And have you ever been exposed to the idea that switches are self-learning? Does that sound familiar? So switches learn what's on the network by just observing. No one has to tell them. No one has to program it. You can take a switch out of the box, plug it in, turn it on, and it will quickly learn where things are. But until it learns, it doesn't know. So A sends a packet to B. It arrives at the switch in the middle. Where will the switch send it? It'll broadcast it to all the other places. It'll send it to B, C, and D. So now B sends something to A. Where will the switch send it? Only to A. How does he know A's over there? Because he saw a packet coming from A. And he learned where B was only when B sent something also. It learned that, oh, next time A sends something to B, he just showed me where he is. But until you know, you broadcast it. So it's not the destination address that teaches you anything, it's the source address. That's one very helpful factor in having source addresses in there. It also handles encapsulation of all the other junk. We use the word frame always, and it doesn't really care what protocol you use. You can use Ethernet or Wi-Fi or whatever, whatever you want. And the layers think that it's frames that are going across, not bits. So does it look any different? Well, from a link standpoint, no. It's the same number of hops. It's the same links as before. That makes perfect sense. Wherever you were sending the bits, well, of course, that's where you're going to see the frames eventually. I mean, that's why you put the bits on that, is because you had the frame to send. So, of course, they're going to be on the same link. You're not going to have the frame on one link and the bits that are inside the frame on another. In fact, they're so intimately connected, very often you just see layer 1 and 2 collapse together, like with the Ethernet spec. And they're going to follow along, but now you've got this little header in the front with the source and destination. And again, it's the frame. Bit at the first layer, physical, frame at the data link. For the network layer, you've got logical systems and something that will look at those addresses and decide where they need to go. That was Paul Barron's big innovation. Make every device capable of forwarding packets with a judicious guess of which way is the right way to go. The network layer calls these datagrams. You will usually hear people call everything above this packets. Application packet, transport layer packet. They'll just misuse the phrase. Doesn't really matter that much, but it is technically called a datagram. So if I want to be really specific about what I'm asking, so you know what layer I'm talking about, I'll ask you about datagrams if I mean layer 3. And the thing about datagrams is each is transmitted separately. So because it's the routing table that's going to specify which link to go over, and therefore specify which link a frame needs to be sent over, and therefore where the bits need to go, the routing layer has all the control. It decides which links will get used and which won't. And so it can change its mind and send some packets, some datagrams, some way, and other datagrams another way. So the major difference is this time the communication is end-to-end, because the source and destination address at the network layer is always of the end systems. never of the intermediate systems. And it gives us a very profound dilemma that we'll learn about soon. Because we really need to tell the network the address of the router that we're trying to reach next. And that router has an IP address. But if my header has room for one source and one destination IP address, and I'm telling you it's got to be of the end systems and not of the router, where are you going to put the router's IP address? It can't go in the header. If it doesn't go in the header, how is anyone going to know where to send it? So that's a dilemma. That has an elegant but confusing to some people solution. So we'll spend some time making sure it makes sense. It's kind of an elegant workaround a little bit. But at the end systems, devices think they're exchanging datagrams. So communication is end-to-end. They do go through the routers. This is the last layer that the routers will also have when we teach you about TCP/IP. Now the thing that's changed also visually is there's one implementation of the network layer on each device, regardless of how many links they have. So if I have that Nexus switch and it had all those connections, there is one implementation of IP for all of them. It can take packets from any of these that get turned into IP datagrams and make a decision about which other one to do. So it's like the telephone operator. There's one telephone operator at the hotel. And have you guys ever stayed at a place that had a really old telephone system? It would have to be like a historical hotel or something. So they used to have switchboards at the front desk. And they had cables with looked like headphone jacks. And they would pull this cable out, it was spring-loaded, and plug it in to your room and connect the call. It was unbelievable. The telephone person was physically connecting the cables together with every single phone call. It was incredible, but it was also fascinating. And I remember vividly, I don't remember where, but I remember vividly staying in hotels and my dad having to come and drag me away. Okay, I should have known then I was going to work for the phone company, right? So I was like fascinated with it even then. So that sometimes is a good analogy. If I can find a good diagram of one, sometime I'll do it. I'll show you guys. So here the logical connection at the datagram layer, because the header only has the end system's IP addresses, the belief is it's just one hop, one path from one end to the other. I shouldn't say hop, I could just say one path to the other end. And here's the path it takes. So I'm kind of building up to that dilemma. Transport is worried about process to process. So you can have lots of programs on a computer speaking over the internet. Each one has a different identity in the transport layer. They are all using the same IP address. Your phone right now probably is sending things from 5 different programs to 10 different places. The time, the network authorization, update packets. Your app store is probably updating an app right now. Maybe you left your email open, it's checking that every couple of minutes, etc. You know, lots of stuff going on, but they're all coming from the same IP address. So how do we keep them apart from each other? Well, why do you need to? When the packets arrive, you got to figure out, okay, mission accomplished, you made it to the right system, but does this go to the email he had open, or the browser she was running, or where exactly? Port numbers, transport layer addresses tell you that. That's what port numbers do. So again, that's another layer where you once again add flow control and error control. So we didn't see that in the network layer. We saw it at the data link layer, and now we see it again. So layers 2 and 4 are where that's done. You can add it again at the top if you want. And you're also responsible for putting things back together if they got split up. So we call these in TCP a segment. And the transport layer, if it's asked to, will deal with problems. It doesn't have to deal with a frame not being transmitted correctly on the physical link, because the data link layer will do that. That much you get for free. But anything beyond that, you don't. Like if it gets lost somewhere along the way, it gets dropped out of a buffer, And you'll have to loosen it yourself. TCP and UDP, there's a third one that's widely implemented, and there are lots of others. I don't know how many versions of TCP there are, hundreds. We usually teach from a couple, but you may have an implementation on your computer that can support 5 different versions of TCP. So there's no telling. Okay, here's what it looks like. The big difference here is this is implemented only on the end systems. So these orange boxes are only at the end. Everything else looks the same. And when I add on the application layer at the end, I'm going to skip session and presentation, and we'll move to TCP's application layer. We like to say it combines all 3, but I can make the argument that TCP does some of that stuff as well. We call these messages. The applications send us messages by using the socket library call. They pass us a message that they want us to transmit to some other computer on the internet. So those are messages. So do you guys think you can remember from the top down what these units of information are called? Application layer has messages. What about the transport? Okay, segment. Anybody remember for the network layer? Yeah, very good. Okay, what about the data link layer? Frames. Would be helpful if I put an R in there. And at the physical layer, otherwise it's farms. Physical layer, what's the unit of information? Bits. So 8 bits make a byte. What do 4 bits make? Yeah, good. You guys know that. I can't believe that. Usually, isn't that crazy? A nibble. Yeah, we don't ever use that. But it's so funny that why not say it, right? All right, great guys. You guys remembered a lot of this stuff. Diagram looks the same there. So let me ask you, if at some point during this connection a router decides to change paths, and instead of using this set of links that we've been looking at the whole class, if the router decides that one of the packets is going to take this route instead in the middle of your stream, what changes with this diagram? So first things first, where is the change in the diagram that I've drawn? So router 3 goes away. Is that right? And this becomes router 2. So it's not going to go through any of these layers for 3. It's going to go through all of them through 2. Anything else? No. Just that simple. That proves to you, if you see that that's just that easy, I got rid of this and I replaced this, so I go up to the diagram and I scratch out R3 and I write in R2, that should prove to you, if you can remember this, that these guys have no idea what's going on inside the network. They have no clue what's happening, because you just changed the route and you didn't have to touch anything on the ends. Right? It can happen in the middle of a stream. In fact, nothing here or here had to know which boxes on this diagram see that there's a change besides the ones in R2. Obviously, all of these figured out what was going on. Who else knows? Physical in which device? Yeah. Anything else? That's exactly right. That's all that has to change. So maybe the new link, so you see it's leaving R1 out of a different port. Maybe this one is wireless and this one was fiber. Those are totally different. Different chips. Not going to have the Broadcom Ethernet chip in this one. Maybe you would over here. So everything's going to be different. It's a different network card. So it's a different layer, but you know, depending on the technology, it will usually suck in the data link layer with it. Because usually we build these as a single unit. When you buy an Ethernet card, it also takes care of generating the sinusoidal signal. There's not like a separate last implementation you make. So usually these are together. You'll never get counted wrong for combining those together because it's almost always correct. Oh, I did too much. Well, now I've even erased the palette I was on. Okay. Too happy with Control Z. Okay, you've got it. So if a network has N links, how many physical protocols are being run? Not how many implementations there are in cards, but how many protocols are being, remember a protocol is between two people. It includes both ends. If you read the RFC for a protocol, it tells both sides what to do. So how many times is that happening? One per link. So just think about, you know, here's my, I want to paste it in again. The President of the U.S. shakes the Queen of England's hand. The Queen of England then turns around and bows to the Japanese Prime Minister. He turns and shakes the German Chancellor's hand, who then turns and shakes the Mexican President's hand. So there are people helping to make sure they're following exactly the rules here, here, between pairs. Whoops, that one was not drawn right. Here and here. So it's how many links. Remember, the book ignores this as something dividing a link. That's a mistake. So these should be links as well. They have to buy those chips there as well. They think they're implementing it. I don't know why Florzon doesn't. Okay, do you need a network layer for devices on the same link? On TCP/IP and the internet, let's assume. Do you need a network layer for devices on the same link? Yeah, it's kind of asking the same thing, but if you look at our diagram, it ought to help. So just ask yourself the counter example. Is there any device on this network that doesn't have the network layer implemented? I mean, this thing is called a network. Shouldn't everybody have the network layer? It's the name of the thing, right? It should be on everybody's badge. So yeah, in TCP/IP, you need the network layer, except for switches. You don't have to have them implemented if you want there. But, you know, we kind of ignored those in this example. All right, let me get back over and wrap us up here. All right, we got those. You guys have that already. So physical addresses are not permanent, but we think of them as such. There are devices that can change them. You're supposed to buy them in blocks from the IEEE. In fact, if you go out and ask, you know, where can I buy a block of MAC addresses, and hopefully the crappy answer is there. Oh, thank goodness. IEEE's got the top hit. They sell them. You can buy them. In fact, one of the fun things I'll have you guys do, assuming it doesn't depend on something on a government site in the U.S., is tell me where your MAC address for your favorite device, whether it's your phone or your tablet or your laptop, where is it registered? It's kind of like ships. You know that most ships in the sailing world are registered in the Bahamas. Do you know that? The vast supermajority, no military ships are, because they're, of course, going to fly their own country's flag, but most ships are registered with Panama. Why? Cheap. They charge less. They'll enter you into the worldwide registry of ships for less than anyone else. And you have to fly their little flag, but, you know, that's the vast majority of ships. You'll find the same thing is true for MAC addresses. So most of you will be surprised by probably by where you find yours is registered. Okay, the format varies depending on the type of implementation, and you will see in some of the protocols that we learned this semester that there's room for other size MAC addresses. All we'll usually see are 6-byte addresses with 12 hex characters, but there are others available out there. So here's an example. Local talk had a 1-byte address. Every time you plugged a device in, it would just be dynamically assigned a new one. And that's what it used as long as it was plugged in. And it would change because it didn't really matter. Okay, node with physical address 10 sends a frame to node 87. Nodes are connected at the data link layer. 10 and 87 are the only addresses needed. In most data link protocols, 87 comes first. What does that mean? It means if I go back to the diagram and I'm looking at the packets as they go across the wire, and I'm watching the bits inside the Ethernet frame, somewhere in there are the source and destination IP addresses. If this is the first bit to arrive, and this is the last bit that's going to arrive, and this is my finish line here, with a little checkered flag at the end, let's see, make sure it says what I got it here. Yeah, so I'll make sure I didn't write the question wrong. The destination address comes first, the source address is different. In most of the other protocols you'll see, it's the way you'd normally expect. Source first, destination second. So why is it this way with the data link layer? If it's different from everyone else, there's got to be a good reason. You should always assume if you can't think of an obvious answer, you've got to believe there's got to be a really good one, or they wouldn't have done it. Stuff's been around for so long that if it was a dumb reason, we would have killed it off by now, surely. Hopefully, that's the assumption you should make. You have a suggestion? Source. Oh, sorry, destination, yes. Now, so this stuff comes fast, right? 10 million bits a second, 100 million bits a second. You don't have very much time to make up your mind about what you want to do with the frame once it arrives. And you certainly don't want to wait around until the whole thing gets there. So as soon as the first few bits of the frame arrive, you know enough to know whether it belongs to you or not. And if you think about what goes on at layer 2, you can have a multiple access network where other people see copies of your frames. Like in Wi-Fi, you're going to see copies of everybody else's frames. So we'll have to make that part of our story more complex next time. But for now, I've given you the impression it's always one source and one destination. That's always true for now, but it doesn't mean those are the only people who are going to see the sine wave. Other people may see it as well. So how do you keep your PC from collapsing as it tries to handle all of the data that all of us are sending on Wi-Fi when you have an older PC and it can barely keep up with your browsing, let alone dealing with all the packets everyone else is sending? Well, you deal with it in hardware to make it fast, and you only keep the frames and pass them on up to the next layer that belong to you. The rest of them you discard, you ignore. So if a frame arrives and it has your MAC address on it, you will keep it. You will send it up to IP, assuming it's not corrupted or whatever, or wherever else it needs to go, often IP. Are you going to keep copies, or are you going to process and send up any other addresses? If a frame arrives and the very first bits are the destination address, and you see that it's your MAC address, you'll keep it. Are there any other MAC addresses that you'll match for, that you'll keep as well? broadcasts. That's the exception. If it's all Fs, all ones, you know, remember the IP broadcast address, 255.255.255. In Mac, we have them too. It's all Fs. FF:/FF:/FF:/FF:/FF. And that's a broadcast address. Ethernet can broadcast also. And when you really want something to get out to everyone, you'll do it. So let's go back to the switch example and explain how this is different than what we talked about before. When we had the example earlier with A, B, C, and D, do you remember? And we had the switch in the middle, and A was trying to send something to B. The frame had B's MAC address as the destination. We'll figure out how he got that later, but he knows that he wants to send it to B, so he sends it out with the destination MAC address of B over here. The switch has no idea where that is, so the switch broadcasts it on every wire. But it doesn't do so by changing the destination MAC address. It leaves the destination address alone, still as B's address. It just electrically copies it to the other links. Well, to all the links, because it doesn't know where it is. And then each link, each computer is going to receive a packet that has B's destination MAC address. And each of them will look at the first few bits and see that it's supposed to be for B, or it's not his MAC address, so it's not a match, and they will ignore it. And therefore, they will never pass it on into the operating system, which is running as software, and you will never overwhelm your implementation of IP. IP cannot handle all the frames that are flying around that the hardware can handle. It's orders of magnitude faster than hardware. This is why we build Ethernet in hardware. There's nothing else fast enough. Make sense? So somebody wrote the code. Then once he figures out where B is, then he'll just neglect to make copies of it over here and just will send it where it needs to go. If, on the other hand, A now is looking for a DNS server, and he doesn't know what the IP address is, so he broadcasts out, or maybe he's trying to get an IP address in the morning, he's using BootP, and he broadcasts out, or DHCP, and he's going to send that to wants every machine on the network to receive it. Maybe by then the switch knows exactly where B, C, and D are. He's figured it out. But A doesn't know which one of these computers runs that protocol. It's an application layer protocol. How in the world would the switch know? Switch doesn't even have the network layer implemented, let alone the application layer. So A is going to send it with a broadcast MAC address. And just like before, the switch will send it everywhere, but this time it will have a different MAC address in it. It'll have the destination broadcast MAC address. Does that make sense? Everybody get that? So just because the switch is copying frames doesn't mean it's changing anything. If it's really supposed to be transparent, it should never change anything. The only thing you should be happy with it doing is either sending something or just choosing not to send it. But that's not changing what's in the frame. That's the way we look at it. Okay? Yes? Yes? Those are both ways that if you looked at what was happening on each of these wires, in both cases you would see a copy of the packet. Before the switch knows where B is, he has no choice but to duplicate the frame on every wire. So you will see it on all of them. And later, if he sends a real broadcast, then you'll see the same thing. It'll be sent to all of them. Right? Routers will not. We'll talk more about that, but probably not today. Okay. All right, so this basically shows you that when you send something, and assuming the switch forwards it on to everybody on the LAN, when 10 is sending to 87, the destination address comes first, and 28 will recognize that it's not 87 and will drop it, and 53 will recognize that it's not 87. These are fake-looking addresses. No one has an address of 10, 28, 53, but this is thankfully what they used instead of a real MAC address. I will do the same thing on homeworks and exams. If I draw you a diagram, I am not probably going to ever draw out all the addresses unless I'm nervous that it won't be clear. I'll usually do something like .1/A, .2/B, and I'll tell you, we'll have practice. This will be the IP address, and this is supposed to be the MAC address. But I try to make things simpler, and I have absolutely no problem when you answer problems if you make them super simple as long as I can tell what you're trying to say. So if the only difference between one IP and address is the last part is a .1, then just say that. Do not waste your life drawing out like all this, no extra points for that. But you're not going to get penalized. Just make it easy. That's just silly work. So most network addresses use 6 bytes for MACs. Okay, there are exceptions to this, and we can have what are called multicast addresses as well. You guys know what unicast are. Those are like sending from my number to your number, intended for just me and you. And we just talked about broadcast, but you've seen that plenty of times before. There's a third variation called multicast, and that's typically used for media distribution. So an example would be if you're watching the Rayados game, and everybody in your apartment complex has Cablevisión, and other than that person watching the Tigres game, everybody else has got the Rayados tuned in. Then how many copies of that signal does the cable company need to transmit down the wire into your building? 1. It's the same game for everyone. So why not just send 1 copy of it? So you don't really want to broadcast it to everyone because maybe some people really are watching something different, and that's not what they want. But everybody who's watching the Rayados, they will send a signal back these days with their cable box that says, what is the address for the Rayados broadcast? And they will tell them we're using the following network number. So it adds a third type of address that your system will pay attention to. So it'll pay attention to its own, to broadcasts, and if it's taught to, it will pay attention to multicast addresses. This is how routing updates are distributed among routers. They belong to multicast groups. One of them sends it, and only the other routers see it. Only they get it. So you don't have to send it to each router at once, and you certainly don't want to broadcast it to everyone on the network. You put it in that multicast group, and it propagates its way through the network. This is done in the core. It never reaches a host, an end host. The edge routers will never send it beyond. They know they're at the edge. They'll never send it beyond there, because we don't ever want users getting those updates. It's a security risk. Okay, so Ethernet will do all 3. Some things don't. Okay, logical addresses are 1 layer up. Those are the IP addresses. So I don't think we'll have time to go over the dilemma I talked about, but I'm kind of debating it actually. I might want to breach the topic just a little bit, just to remind you as we set it up. So here you see an example of what they're doing. A10, it looks like a hexadecimal character, so that's probably the MAC address. 10, these are always numeric, that's got to be the IP address. So that's what they're doing. So there's a logical connection somehow from here to here, but this diagram only confuses the things more because what it's not showing is that this sender puts an IP datagram on the network that has this receiver's IP address. It does not have the router's IP address here, nor does it have this one. So how does it get to this router? Some piece of software in this computer has to decide, okay, someone gave me a packet. What am I supposed to do with it now? Guess I better send it on the network. Okay, well, I've got Wi-Fi and I've got Ethernet. Which one do I send it on? Well, you've got your little routing table. What route does the table tell you to use to reach this destination of receiver down here? Well, it says I'm supposed to send it to a router with this IP address over here. Okay, well, that's on Wi-Fi. So that's all I needed to know. I will send it out over the Wi-Fi network. But who does he actually send it to? He can't send it to his IP address because it's got this IP address. So we'll talk about exactly what happens. Unless somebody remembers, that would be cool. But it's important to understand that detail. You'll get lost on the exam, on homeworks and things, and debugging networks. If you use Wireshark, you will not understand what in the hell is going on if you don't nail that particular topic. So we're not going to cram it in the last 10 minutes when you guys are hungry and tired. And I'll probably screw it up explaining it, so it's risky for me. Okay, a few last slides. The physical addresses change from hop to hop, but the logical address always remains the same. That's a different way of saying the same thing. The logical address is the IP address. It leaves the PC at the origin, and the destination never changes. When you send a packet to Google, you have no idea what routers it's going through, nor do you care. You put Google's address in there and let the network take it from there. And no one changes where it's going. Everybody needs to keep there that it's going to Google. Okay, port addresses are one layer up, and this just keeps track of different programs. That one's not at all hard to understand. There's nothing really tricky about it at all. This is like giving you an apartment number in the apartment building. If mom mails you a letter, she has to put the apartment number on it. The numero exterior is not enough. She's got to put the other one in there, or how are they going to know who to give it to? Like the mail carrier may drop it off at the building, but then the office needs it. So it's no more complicated. We'll end with showing you guys a little fun video to show you what vacations for my family are like with me. It's a little sad. Here we go. Okay. I visited my son the semester he took off and went to Florence, Italy. This is when I still worked for Silicon Valley. I would not be sending him this now. He could go to Florence, Texas now or something, if there is one. So I got to go to Florence, Italy for the semester to the School of Arts. It's been there. The David is there, for example. You remember the David, right? In fact, he took me to a really interesting museum. We went to a museum that has all the arms and the heads that are missing from all the other statues and all the other museums. That's a Stephen Wright joke. Anybody funny? No? Get it? Okay. So we were walking along, and I was noticing something interesting, and okay, we're going to do a little quiz here on... So I'll narrate since you can't hear. Maybe the people on WebEx can. So not surprisingly, I find a McDonald's, and that's a number 6, and it's red. Here's a number 31, and it's blue. Okay, that other one was not 6, it was like 60. Hold on a second. Ah! Stop! I'm going to keep track. He's over here like, what's he doing? So I'm doing that as well. So we have red and blue. So far we've seen 60 and 61 on the red side, and I think it was, what was it on the blue side? 31. All right, I think I got it right here. Okay, 61 there, and where is it? Oh, maybe, I don't know what that one was. 59 maybe? 29. 55. 27. I'm not positive what it was. 53. Oh, yeah, okay, well, if it's down, yeah, that would make sense. 23, 25. 51. 'It's on the other side of the street. So it's a form of addressing. What else do you notice about the two ranges of numbers? Well, that's like in every country, right? Odd numbers on one side of the street, evens would probably be on the other. It was too cold and I wanted to get back inside. So these people are fine. I mean, you didn't have her jacket closed here. I'm like an Eskimo. I mean, that's the whole thing. So what about where they're positioned on the wall? What's the difference between this number and this number? One's higher. Which are higher? Is it always the red ones that are higher? Yes, it is. So in an older city like this, what's the difference between what you find down low in a building and what you find up high in a building? Including in Monterrey. Calle Morelos, what's on ground level? Calle Morelos? No? Nothing? You guys don't know where that is? No? Okay. So it's the pedestrian street in the center of Monterrey. All tiendas. What did you say? The white people? What? That's what it sounded like. Yeah, so but they're there for the tiendas. Right? So it's all shops on the first floor. People live there, the buildings are taller. They all live upstairs. Right? Businesses. Yep. So they gave different addresses to businesses than people. So the apartments up above, it's not me, guys. This is Italy. Italy's inefficient in some things. It's a big clue, okay? The residents have red numbers up at the top, and on the same street, you have a completely different set of numbers. I'm sure they overlap sometimes. It must be really confusing. So it's not the worst I've seen. The worst I've seen is in Japan, where until the United States occupied them at the end of World War II and forced them to put addresses on a 100-block basis, and every place you've ever been in the world, addresses, unless you've been to Japan, and maybe even then, they do it in a 100-block basis, and what that basically means is depending on how far away you are from some government-designated point, usually City Hall in the center of the city, that governs the address you're going to have. So people with addresses of 0 to 100 are in the little circle, from 100 to 200, from 200 to 300, and so on. And as you move further away, your addresses get bigger and bigger. So we're at 6,885 by the time you get here, for example. Right? So that's the 100-block system. And, you know, we see it because it's a grid, but all the electric company does, which is usually who assigns addresses, not the post office, which is really kind of interesting. They just look to see what circle you're in, and that whether you're north, south, east, and that governs the numbers you get. They assign them that way. Right? In Japan, they numbered them since eternity. This was the first one built in the city, so it has address 1. This was the second one. The third one was over here. The fourth one was here by Colonia. So this explains in part, you know, it's kind of a chicken or egg problem. Is this why they're so insular and so homogenous, and there's very few foreigners? There's very few people that become Japanese citizens that are not Japanese? Is that why? Is that why you know the policeman your whole life? It's the same policeman for his whole career, and the same baker, and the same restaurant, and it's the neighborhood everything, the neighborhood school. How could you find anything outside your colonia? So you can have on a street building 30, the next address can be 4, and the next can be 60, and it's not because of the Italy example. So this drove the United States Army insane. And so they made them take some major boulevards and implement a 100-block system. So General Douglas MacArthur Boulevard in Tokyo is numbered with the 100-block system, and there's a few others. But when I had a friend, before there was Waze and Google Maps and all that, I had a friend who worked at Sun Microsystems and had to take a trip, and the taxi driver was not very familiar with that colonia, And so he opened his trunk and he had these stacks of big directories of where everything in Tokyo was. And he had to get on the radio and call another taxi driver over, and they spent 15 minutes figuring out where the heck this place was, this office that he was trying to get to. Any hotel they would have known, he'd have been better off saying to the people he was meeting, I'm going to this hotel, you come and get me and take me back where we need to go. So it's just fascinating that this is an economy that is among the most efficient on the planet, that dominated electronics manufacture for a long time, and yet they don't have any kind of scheme to address homes. So you'll find all kinds of addressing schemes around the world. Fortunately, ours are pretty sane. Where it does go crazy is some people don't bother buying MAC addresses. They just use ones that they want. I mean, what are the odds that you're going to get caught? The only other thing that's ever going to see it is the one device at the other end of that connection, typically, right? So it's possible that it will happen. You could end up with two devices and see all kinds of crazy conflicts and things. And it's really unfortunate when it's your own fault. Cisco shipped spreadsheets to Foxconn of MAC addresses they wanted installed in devices and shipped the same sheet to two different plants. And so we manufactured two different sets of devices with the same MAC addresses. And they ended up on the same network. A pair of them did. And we're like, it's like Homer, you know? So, dope! I know he doesn't say dope in Spanish, but I haven't mastered that sound yet, so I'll give you the American Homer Simpson sound. Okay, guys, that's it for this week. Watch for homework, and any questions? Still mostly new stuff? Deeper than you knew? Okay, is this helping clear up any holes, missing gaps? Okay, hope so, hope so. All right, have a great weekend. See you guys soon. Not yet. You will.